Hello guys, welcome back to the wireless channel. I'm Niklas Pühling, and today I will present another of our papers that will be presented at the IEEE WCNC presentation. And the topic is about, as the title suggests, it's egoistic MDS-based rigid body localization, one work that we did together with our partners from Continental. So let me just start here with some introduction to RBL. And what is RBL in general? So localization is needed in many fields such as industrial automation, robotics, but also vehicular networks. But the problem is that single point localization is often not sufficient in certain scenarios. So what's the solution? Rigid body localization, which yields not only the location, which we will talk as the translation, but also the rotation. So you get the position of your target and the orientation, which is nice and also similar to what was discussed in one of our previous videos, actually. So just to get an idea, we talk about this here in this automotive perspective, where you have a rigid body transformation of the car in this case. So you can see the car here at position 0, we call it S0, which is our conformation matrix. We have all of these sensors mounted to the rigid body, and this will then be transformed to this second position as 1, where we apply a translation to it and a rotation. So you transform the rigid body. Mathematically, you can model it as follows. So we can consider in our example, we have 2 individual vehicles with N1 and N2 sensors. That means they don't have to be the same object. It can be one big car, one small car, or even a bike. And then all of these vehicles, so vehicle I can be modeled as a rigid body with N sensors deployed, as you can see in the previous picture. And now the sensor geometry of the I body is captured in the so-called conformation matrix, C1, which basically captures all the positions of the nodes, so all the sensors mounted to the rigid body. Now, this conformation matrix is the original reference position of the rigid body. If we now apply the translation and the rotation to it, we can model it as followed here. So we transform the rigid body by a translation Ti, in this case for the ith rigid body, and a rotation Qi, which leads to this formula here, which we can either model like this or in matrix form if you just want multiplication. Good. Then what do we want to do next? We need to define a measurement model. In our scenario, we consider line of sight cross body measurements. So just a simple distance measurement between sensor M and N, which can be modeled as shown in equation 1. So you have the pairwise distance here, which is defined by the rho. And then you just have some IID zero mean Gaussian noise with some variance defined. And the next, because we need it in the proposed method, we can also define the squared distances, which can be modeled by equation 2. So you just square the pairwise distances and then the characteristics of the noise change, which you can see here below. Good. Next, what do we want to find? We have the line of sight distance measurements. Now, not only of the measurements, but also of the full rigid body system. So you have your whole matrix D here that captures all the distances. You have D1, which are the intra-distances of the 2 vehicles. So the distances of the sensors in the rigid body itself. Then you have D12, which are the captured cross-body measurements. And then we have D2, which are the distances of the second vehicle. And then additionally, this can also be shown in the squared form by equation 4, which you can use for simulations and also later on. Good. Then let's go back to the title. The title was Egoistic MDS-based rigid body localization. Now we will explain why it's called egoistic and how we use MDS, which stands for multidimensional scaling, in the proposed method. So now we can first consider this scenario. Now we have 2 rigid bodies. And the goal is that now we say it's egoistic RBL. We can say we are the truck, we are S1. We know how we look, we are on the street, and we want to now find the target, which is S2, which is this red rigid body. And the problem is, we know how we look, but we don't know anything about the target rigid body. So the conformation matrix with the shape of the target is unknown. And you can also see here in this picture, we do some distance measurements from the sensors. We have the translation of the 2 individual cars, T1 and T2. And you can see the rotation defined by these coordinate frames. And you can see the general translation from our perspective to the target rigid body. Next, we can look at the following parameters and check if they are known or unknown. So we can say T1 is known, Q1 is known, and C1 is known because we say we are the truck, we know how we look, we know where we are positioned. So we know that. We don't know C2, we don't know how the target rigid body looks. We don't know D2, and we also don't know the translation. And how we want to find it, we will present next. So the solution is we rewrite the problem to avoid or approximate unknown parameters. Let's start by remodeling how we look at the rigid bodies. So first we had the two individual rigid bodies, S1 and S2. These can now be stacked into this general rigid body transformation frame. So now instead of S1 and S2, we only have one S. And if you just stack the equation that I showed in the beginning, you will get what is shown here in equation 5. So if Q1, Q2, C1, C2, T1, T2. Yeah, and then just the equation. And what we want to do next is we apply all the assumptions that we know. And what we can find, okay, we said we know Q1, which is just meant to be an identity matrix. We don't know Q2. We know C1. We also don't know C2. And what we want to find next is just the translation vector T. So what needs to be done to find all these elements? First, we can go back to our distance matrix. As I said, we know how D1 looks. We measure D12, and then D2 can be approximated via Nyström approximation, which is a really simple matrix completion method, which by just doing this one computation finds a good approximation of D2 that can be used in this scenario. Next, we can then find the first estimate of the sensor target positions via MDS. You can look at details in the paper. I just showed the final results here in equation 8, where we say, okay, our S is now C1 because we knew it, and then S2 hat is found by MDS. Yeah. And the next, I want to introduce shortly the so-called double centering operator, which is used in the actual estimation. So consider here a double centering matrix J, which is shown in equation 9. And if you apply that to any point matrix X, as you can see here in blue, then you will get a mean-centered version of this matrix X. So you will get an X bar, where the mean is now centered at the origin. And now the nice thing about MDS is actually the relation shown in equation 11, which maps the mean-centered point matrices, so X bar, to the distance matrix. And this will be used then in the next step to be modeled by the rigid bodies and the obtained distance measurements to find an optimization problem where we can solve for the unknown parameters. So if we go back into our previous estimate, so we can plug that into the equation that we have that models our rigid bodies. Again, we have C1, which is known. Then we can stack the Q and the C2, which is modeled, as you can see here. So Q2, C2 is equal to the mean-centered version of the estimate that we found. And now the only parameter that is left that we don't know is the translation, which we want to find. So using the MDS relation that I just explained, we can find the following optimization problem that is convex and can simply be solved by conventional methods to now solve for the translation vector T, which is contained in the S hat. Then we can already look at numerical results. The parameters are chosen as in figure 2. I will also show it again shortly. So we have the conformation matrices here, C1 and C2, which is the truck and the car. And we have the translations and rotation. So T1 is just a 0 vector. The angles are also 0. And then the second vehicle is modeled by this translation and the other rotation. And then for the metric, we consider the RMSE, the root mean square error, epsilon, which is calculated by K Monte Carlo realizations. And again, just to get a picture of all the dimensions that you will see in the results, you will just have here again the picture. So we have the truck and the car, as you see before. Then let's look into the results. First, you can see here the translation estimate RMSE versus the range error sigma, which was shown where we modeled the range error, so the distance measurements. And what you can see first is here some results where we compare to a least square state-of-the-art rigid body localization method compared to our so-called genie-aided version. What is genie-aided? In our proposed method, as I explained, we assume that we don't know how the rigid body looks, so the target conformation matrix. But since to the best of our knowledge, there are no other state-of-the-art methods that also have this assumption, we now feed the conformation matrix to our algorithm, which will give us a so-called genie-aided solution of our method. And you can already see here, it beats the state-of-the-art starting at 20 centimeters, and then for lower range errors, it will outperform it. But then to see, okay, how does the actual egoistic method perform, we can just compare the genie-aided now to our egoistic method. And you can see that it's actually only slightly worse. So the difference of these two lines is just the lower one is the genie-aided, where we know how the target looks. And then the top one with the ball markers is the one where we don't know how it looks. Now you probably already got a few questions and ideas how you could extend this work. And we already did that in a journal extension, which we will show in a follow-up video. But to hint at the journal extension, so currently only a fully connected scenario is evaluated, which means that we always assume that we have all the measurements. But in the journal extension, we considered a connectivity matrix, which is introduced to capture missing links. So then in the distance measurements, you would not get all the measurements, but also a few zeros in it. And then also the incomplete observations can severely harm the performance, as will be shown then. And what we do then is to use some matrix completion methods on the Euclidean distance matrix that can improve the results. And we actually propose an additional estimator that is shown to be more robust to these incomplete observations. And now, thank you for your attention. If you have any questions, let me know. And also here you can see 2 QR codes to the preprints of the articles if you want to take a look.
Thanks, Nicholas. Very good work. Very interesting. I have one question. In the optimization problem you saw, you used to find the Q, the estimate of the rotation matrix.
Yeah.
In the paper is equation 28.
Yes, I didn't show it here because we didn't have any results for it in the paper. But in the journal one, we have some.
Oh, no, in the conference paper itself is also in 28. I was just wondering if you think that that problem as it is right now is an unconstrained optimization problem. But recently working with other things related to this work, we have found out that you could perhaps constrain at the very least to the Stiefel manifold, or maybe some other type of constraints. But that's my question. Have you thought about it? Can you elaborate on the possibility of improving the estimate of the rotation matrix Q by adding a constraint that makes sure, because as you know, that the values of the matrix are not fully independent, right?
Yes, exactly. Maybe to explain first for the others. So what Professor means is that if you have such a rotation matrix, it has to be in the special orthogonal group, which means that if you have Q transpose times Q, it has to be identity. Otherwise, it's not a valid rotation matrix. And yes, that's a really good question. I'm not completely sure. In the paper, what we do is we rewrite an original Procrustes formulation, Procrustes problem, that was meant to solve the problem if you know how the rigid body looks. And I'm not 100% sure if the Stiefel manifold is already incorporated in this Procrustes problem. But if not, then we should definitely consider it, yes.
Yeah, okay, good. Yeah, that's good that you had that in mind. But doing the Procrustes is only a correction after the fact, right? After you have already found your solution to the optimization problem.
Mm-hmm.
And so, and it is well known, not in this particular thing, but in other related problems, whenever you solve something and then you have to clip it down to some conditions, and then typically this is outperformed by formulation of the problem that already forces the solution to follow the constraint. So yeah, I guess this is something for us to look next in this. But yeah, thank you for the question. Anybody else, guys? You have any more questions? If not, then Nick, thanks once again, and I see you guys next time.
Yeah, thank you.